And we are talking about stuff that obviously will be on exam 2. Remember that. Thank you very much. It is spring training, you know, started this week. We might as well look at spring training. That is the Angels spring training part back there, I think. Hopefully next year we get to go, I suppose, in person. So last time we started talking about chapter 3, and that is, again, going to be on exam 2. The only thing from chapter 3, as we talked about last time, that you are responsible for the upcoming exam, which is 1 week from today, I believe, is about electronegativity. So we talked about electronegativity in terms of sort of periodic trends. So really, again, you need to know electronegativity, what it is. You also need to know the periodic trend relationship for the first exam. And then obviously we will talk more about electronegativity here in chapter 3, and the rest of chapter 3 again will be on the second exam. So we just get started talking about bonding, and really bonding. There's 2 types of bonding that we talked about. One is ionic bonding. As we started to get into, ionic bonding is always between a metal and a non-metal. And it always involves really the metal losing electrons and becoming positively charged or a cation, and the non-metal picking up those electrons and becoming negatively charged or an anion, really for those sort of periodic trends that we did talk about. So based on sort of their locations on the periodic table and those periodic trends, as we talked about, essentially our metals are the ones that pretty much are willing to give up their electrons, and our non-metals are the ones that are really able to sort of accept those electrons because of those trends that we spoke about. And that results in an ionic bond, which again is no sharing of electrons. What is keeping that together is the positive negative attraction between those anions, and that's what basically makes an ionic bond. The other type of bonding we talked about, and we'll talk obviously more about as well today as well, is covalent bonding. And covalent bonding is when we pretty much get together a couple of nonmetals. So also related to those periodic trends we talked about in the previous chapter. If you look at where nonmetals are located on the periodic table, they're pretty much all bunched up together there in the upper right. And that means that they have very similar trends in terms of electrons, really. And as we talked about, what they essentially happens is they both, because they're nonmetals, want to hang on to their electrons, and they actually want to bring electrons towards themselves. So what ends up happening, unlike when a metal and nonmetal get together, where the metal's like, go ahead, take my electron, the 2 nonmetals basically decide, well, I want the electron, you want the electron. So the best that they could do is actually some type of sharing of electrons. And that's what's the basis of covalent bonding. And as we will also talk about in this chapter, it is either going to be, as we will see, equal sharing of electrons or unequal sharing of electrons. And that results in really 2 different types of covalent bonds that we see, and we'll talk about, which is polar or non-polar bonds. We also talked about the idea of using Lewis dot symbols. They are also sometimes referred to as electron dot symbols. And those are really the symbols of the elements. We use 1 dot to represent a valence electron. Remember that the valence electrons are the outermost electrons, the ones in the highest energy level, and they are the ones on the outside. So they are the ones, obviously, you can imagine would be involved in bonding. Since they're on the outside, they're furthest away from the nucleus. So when 2 atoms come together, they probably are the ones that are going to come in contact with each other. And we can represent our ionic bonding using Lewis dot symbols, as we did, I think, in the previous one where we left off. Here we're looking at really the formation of lithium fluoride. Lithium, which is group 1, has 1 valence electron, so there's our 1 dot. Fluorine, which is group number 7, has 7 valence electrons. And again, because lithium is a metal, it's going to give up its electron over to the fluorine. And when it does, that's when the lithium actually does become positively charged. The fluorine will then pick up that extra electron, and now it's got an extra electron, and it becomes negatively charged. And it again is that positive negative attraction, which basically holds those units together. The other sort of important thing that we see is that it's achieved in this ionic bonding and really in bonding in general is in terms of electron configuration, lithium goes from its initial configuration, and by losing that electron, it actually backs up to the same electron configuration as helium, which means it's isoelectronic with helium, also means that it has now achieved a noble gas configuration. Fluorine, by picking up that extra electron in the p subshell, goes forward and ends up with the exact same electron configuration as neon. And by losing electrons, by gaining electrons, both the metal and the non-metal here in this ionic compound are both able to achieve the same electron configuration as the noble gases. And that really is the basis of all bonding. Noble gases are incredibly stable, is what everybody really tries to achieve. And in sort of our ionic bond, the way that's able to be done is, as we see here, metals lose electrons to go backwards to the noble gas that comes right before it. Non-metals gain electrons and go forward to the noble gas that comes after it. And again, they both are able to achieve that noble gas configuration. A couple other important things we talked about is when you draw these for ionic compounds, you do need to include the charges. They indicate that there's no sharing of electrons. And a lot of times people will put at least one of them, sometimes two of the ions in brackets. Again, just to further indicate that there is no sharing of electrons happening here. We have a complete transfer of electrons. Any questions on that stuff there that we talked about? Okay. So as I just mentioned, that is the basis of our ionic bond, is that positive negative attraction that occurs. And essentially the way we're able to get that is, as we just talked about, our metals basically on the periodic table back up to the noble gas that comes right before them when they lose electrons. And our nonmetals basically do the opposite. By gaining those electrons, they move forward on the periodic table to the noble gas that comes after them by gaining those electrons. So that is really, like I said, sort of the basis of all bonding, is that idea of really everybody is just trying to get to that noble gas configuration. So let's take a look at another example. Let's take a look at calcium oxide. Calcium oxide involves obviously calcium and oxygen. So again, if we look at calcium, calcium is number 20 on the periodic table. And again, if you were to write the electron configuration, 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2. It is also group number 2, which means it has 2 valence electrons. And again, it is these 2 electrons right there, which are their valence electrons. Oxygen, which is number 8 on the periodic table, 1s2, 2s2, 2p4. Oxygen is group number 6 on the periodic table. That means it has 6 valence electrons. And again, it is actually these 6 right here, which is the valence electrons that we see here. So if we want to represent our sort of Lewis dot symbols to show our bonding that's occurring here, we can do that. Again, calcium is going to have 2 valence electrons, so 2 dots. Again, with our configuration that we see up on top, we have oxygen, which has 6 valence electrons. We'll kind of do it that way. And what's going to happen here is we are going to get those electrons transferring from our calcium over to our oxygen. So maybe one there and maybe one there. And the result of that is we end up with calcium that has now lost 2 of its electrons. And because it lost 2 electrons, it now will end up with a positive 2 charge. We end up with our oxygen that had its 6 electrons to begin with. And obviously, because it gained those 2 electrons, one there and one there, and now ends up with a -2 charge. Again, it is the +2 and the -2 there that is holding that together. There's absolutely no sharing of electrons. And just like what we saw with lithium fluoride, if we see or look at what's happening here with our electron configuration, well, the calcium there just lost the 2 electrons in the box, leaving it as 1s2, 2s2, 2p6, 3s2, 3p6, which is 18 electrons. It has just achieved argon's configuration by doing so. Our oxygen here that gained 2 electrons, those 2 electrons are going to fill out the spot right there. And they will go 1s2, 2s2, 2p6. Again, if we count up the top there, that is a grand total of 10 electrons. And our oxygen here with a -2 charge has just reached the same electron configuration as neon. So once again here, we do see sort of what we talked about earlier, that by losing and gaining electrons here, we have both achieved that noble gas configuration. And again, that's going to make it very, very stable. And again, really pretty much what everybody is trying to do here. Any questions on how we got there or representing this with Lewis dot symbols? And again, really important, especially with ionic compounds, to make sure that you do include the charges there on the drawing. So let's talk about, what happens maybe if we put together a couple of these guys here from the previous 2 examples. Let's talk about what would happen if we put together our calcium, say with we did fluorine earlier. So let's talk about what would happen if we put together those 2 guys. So let's say we put together calcium, which has this, and fluorine, which we did earlier, which has 7. Am I badly drawn one here? Looks like that. Again, calcium having obviously the same electron configuration as we see above there, argon 4s2. Fluorine, basically 1s2, 2s2, 2p5 in this case. So when calcium gets together there with it, it's going to want to lose its electrons. So calcium here will lose an electron over here to fluorine. But then it becomes sort of a problem because this fluorine doesn't have any more room, right? It just maxed out at 8 electrons. And that's problematic for calcium. So if we look at the periodic table, we got potassium, we got calcium. And then if we go backwards, before that is argon, where we're trying to get to. But if calcium only loses 1 electron, it's going to basically move back to potassium's configuration, and alkali metal configuration doesn't have the same ring as noble gas configuration. So that's not really good. So calcium is definitely not going to be happy in this situation because it's only able to get rid of 1 valence electrons. How can we fix that? Well, we have to fix that by having not 1 fluorine there, but we actually would need 2 fluorines there. The second fluorine now allows a place for our calcium to lose its second electron, allowing it now to actually get back to argon's configuration and be happy. And the result of that is our calcium will once again end up with a +2 charge. We will end up with 1 fluorine that picked up 1 electron and becomes -1 charged. We will also end up with a second fluorine that picked up 1 electron and became negatively 1 charge. This +2 charge of the calcium is balanced by the -1 charge there and one more -1 charge, which gives us a -2 charge. All 3 of these guys in this particular situation have just achieved noble gas configuration. The calcium, by dumping 2 electrons, 1 to each of the fluorines, goes back to argon's configuration. Each of the fluorines will put an electron in there, giving it 2, 4, and 10 electrons, which means both of these guys will achieve that neon configuration. And all 3 of these guys have essentially achieved noble gas configuration. This is actually the basis for why when we write formulas for ionic compounds, that we always want to balance out the charge. Yeah, so we don't use any type of lines at all, solid lines. So if you're asking, if your question is, you know, do we do anything like that per se to represent, you know, this? And we do not do it like that, because there is actually no sharing of electrons happening here. It's an ionic compound. So when you draw those solid lines between elements, it represents that there's some type of sharing of those electrons. And this is definitely not the case this here. What's actually happening again is that attractive force. You may sometimes see people draw it like in a row like this. You may even see something like this, you know, with all these brackets. But we would never in this type of situation draw lines between them, because again, that would imply more that the electrons are being shared. Exactly. So these are ionic, so no sharing of electrons. We will use lines when we do actually more covalent compounds. Yeah, in just a second. The why does the calcium get a +2 after the configuration? If you're asking why does it get a +2 charge? Is that what you're asking?
Yeah.
Yeah, so it gets a +2 charge because it basically lost 2 electrons, right? So every time we lose an electron, we become more positive. So it lost this first electron, for example, to one of the fluorines. It then lost that second electron to the second fluorine. And now it basically has more protons than neutrons. So in this situation, this calcium still has 20 protons. But because it lost those 2 electrons, it only has 18 electrons, which are negative. And that's why it ends up with that +2 charge over here. Other questions on that? Okay. So, and again, also to sort of that earlier question as well, that's again why it's important to make sure when you're drawing these, again, for ionic compounds, that we do include the charges, because in addition to not really using lines to connect anybody, by including the charges, you're basically telling people that we have formed ions here. So something has lost electrons, something has gained electrons, and it's that electrostatic attraction between everybody that's essentially holding, you know, that sort of unit together, or that bond together. Other questions on that there? So, like I was saying before, this may sort of be recognizable to you if you remember, and obviously we'll talk about later on when we get back to this chapter. But when we do write ionic compounds and we write formulas for ionic compounds, the goal is to make sure that all the positive charges from the cations and all the negative charges for the anions basically equals 0 when you put them together. And the simplest way you could do that. So that's why when we take something like calcium that has a +2 charge, and we take fluoride, which is group 7, has a -1 charge, when we put those guys together, we have a +2 and a -1, which means we actually need 2 of those guys to balance it out. And that's why the correct formula here is CaF2. The Ca indicates we have 1 calcium and a +2 charge. The F2 means we have 2 of these fluorides at -1 charge. And the real reason that when we put a metal and non-metal together and we balance out the charge to 0 is actually what we just drew here. The purpose of it is in order to balance it out to 0 in the simplest way possible, that is ensuring that all of those ions, the positive guys and the negative guys, they will all essentially achieve noble gas configuration. So that is really the true reason why when somebody tells you when you write an ionic compound, make sure the positives and negatives balance each other out to 0. And the real reason for that is because when you do that in the simplest way possible, you're allowing each of those guys, when they form ions, to all 3 of them in the case of this calcium fluoride, all 3 of them basically to achieve noble gas configuration. Any questions on ionic bonding, how to represent it or show it? Okay. So again, take home here on ionic bonding, a reminder that sometimes people oftentimes forget, absolutely positively, no sharing of electrons happening here. So just a complete transfer of electrons from our metal to our non-metal in this particular case. So then let's talk about then covalent bonding. And as was the question earlier, this is sort of what we do use here to represent sharing of electrons. So when we get to, my lines and stuff are all off here, so I'll fix them. But covalent bonding is between basically 2 nonmetals. And again, as was mentioned earlier, because it's between really 2 nonmetals, there is going to be a sharing of electrons is going to happen here. Again, because our nonmetals on the periodic table are up there in the upper right, it means they all share very similar periodic trends, which means the best that they're going to do is we're going to decide to actually share electrons. So Gilbert Lewis suggested a role of electrons as basically a sharing of electrons when a bond forms. And I'm just going to kind of scratch this out since all my dots got all over the place here, got a little off centered. But if we look at 2 hydrogens, each hydrogen would have 1 valence electron. And different, because they're both hydrogen, they have the exact same periodic trends, basically, which means they're basically going to each want to keep that electron because they're both a nonmetal. So what's going to essentially happen here is these 2 electrons are going to actually be shared between the 2. And when they come together, we could represent that sharing by putting the 2 dots between them. And when we count sort of, what electrons count for which, these 2 electrons which are being shared count for the hydrogen on the left. The 2 electrons in the middle there that are being shared also count for the hydrogen there on the right. And we could also represent this by a solid line between the 2. And again, that solid line means that 2 electrons are being shared between the 2 hydrogens in this case. So one line, as we will see, is a single bond. And again, results in a sharing of 2 electrons. We will see a little bit later on as well. 2 lines is a double bond, which means we're sharing 4 total electrons. And 3 lines is a triple bond, which means we're sharing 6 electrons or 3 pairs of electrons. So in this case, because there are nonmetals and they share those similar trends, in the case of hydrogen, they share the exact same trends, obviously, because they are the same element here, we do end up getting those sharing of electrons. So that's a very good question about the octet rule, and we're going to get to the octet rule here in just a second. But to sort of answer your question here, when we do look at hydrogen, for example, the hydrogen on the left is sharing 2 electrons. Hydrogen on the right is also sharing 2 electrons. If we look at the periodic table, this is our good friend hydrogen, right? Number 1. And if you go to the right of hydrogen on the periodic table, that is helium, which is number 2. So for hydrogen to achieve noble gas configuration, it actually only needs to get to helium. And that's why hydrogen will only and should only have 2 electrons, because essentially it only needs to get to helium, if you look on the periodic table, to achieve that noble gas configuration. So actually here, by sharing those 2 electrons in this case, both hydrogens achieve that noble gas configuration by doing so. You are correct, I think, with your question as well. And again, we'll talk more about it in just a second. But everybody else, as you go further down on the periodic table below helium or past helium, everybody else will then head up to 8 valence electrons, because that's the noble gases that come after them. But helium only has 2, again, still a noble gas, but only has a grand total of 2 electrons. And since hydrogen is the only element that comes before that, it only needs to go 1 step kind of forward to get to that same stable arrangement, and only needs 2. This is, as we will see, sometimes referred to for hydrogen known as a duet rule, which basically means it just needs 2 valence electrons pretty much to be happy. And as we will see, everybody else will need that magic number there of 8. Other questions on that? Okay, so this again is a covalent bond. We have that sharing of electrons, and those electrons count for both sides. As we'll talk about in this chapter, the sharing may be equal sharing. It may be some unequal sharing. But if you do have a covalent bond, there's some aspect of sharing that's basically occurring here. For it to be a covalent bond. And again, that is very different than an ionic bond, where there's absolutely no sharing of electrons that are basically occurring here. As for simplicity, like I said, you can use lines instead of dots. If you like dots, you can use the dots instead of lines, but you can represent it either way there. And again, I apologize, but my lines got all out of whack here, but there should be a line between those two right there. So as I mentioned before, in a covalent bond, we have those sharing of electrons between the 2 atoms. So you could kind of think about, when you have, say, like the hydrogen one that we just looked at, we have basically these electrons between them. And really, there's a nucleus, right, at each of these atoms. The electrons are negative. So, these electrons here are going to be sort of attracted to the hydrogen's nucleus on the left, but these same electrons are going to be kind of attracted to the hydrogen's nucleus on the right. So you got kind of that, I'm attracted to the left there, I'm attracted to the right, and that's sort of what keeps those things locked in place and keeps those guys together, is that kind of mutual attraction that's happening between each of the nucleuses there, and it keeps everybody pretty much in place and kind of keeps that covalent bond basically going. It does have to do polarity. So we're going to talk a little bit about, what type of bond this is a little bit later on in this chapter as well. But this is a type of covalent bond, which is sometimes referred to basically as a nonpolar covalent bond. We would expect here equal sharing of electrons to be occurring here. So there is some to do with sort of the attraction to those nucleuses and those electrons. So if we take a look at another example like F2, fluorine has, again, our 7 valence electrons here. So again, because they're both fluorine, what we're going to get here is essentially our 2 electrons being shared. And what we see happen on the right-hand side is, again, if we count up for our fluorine on the left there, it's got 8 electrons. And again, those 2 electrons in the middle will also count for our fluorine on the right. And by sharing those electrons in the middle, they both hit those 8 valence electrons, again, basically getting both of those guys over there to group 8. and the noble gas sort of configuration in this case. Again, really moving them forward, right, to our noble gas. Again, we are obviously past helium in that point, and that's why everybody else other than hydrogen essentially will always need sort of 8 electrons. Again, you could represent this like on the left there with all dots are the electrons involved in the bond. You could use a line to represent it. Again, either one's fine. I personally use the line most of the time, but you can, you know, kind of do the dots all around if you want. When we do look at something like fluorine, for example, there are some different types of electrons that we see. And if we look at some of these different types of electrons, we have all these electrons on the outside that are dots, and they are not involved in any type of bonding. How do we know there's no bonding happening there? Well, there's like nothing on this side. There's no other element written there. So obviously there's no bonding happening there. These guys are what are referred to as lone pairs. If you're kind of old like me, I suppose. They are also what are referred to as non-bonding electrons. Very creative name there. And they are the electrons that are not involved in bonding. I personally will probably call them lone pairs a lot, but most books nowadays and stuff call it non-bonding electrons. So if I say lone pairs, it's the same thing as non-bonding electrons, basically. There's also some electrons that are obviously involved in the bonding right there between the two. It also has a very creative name. These are what are referred to as bonding electrons. Yeah. So non-bonding electrons, much like the name implies, has no bonding involved, or there's no bonding involved between the elements there that are sharing those electrons. There would be no two elements sharing in that case. But bonding electrons are the ones that are involved in actual sharing between two elements. So we do draw Lewis structures as a nice representation to help us, again, see basically covalent bonding. And again, because we're dealing with covalent bonding, we're dealing with some sort of sharing of electrons. We do draw those lines. Obviously here, there are no charges on anything because there's no ions being formed. So it should be no charges in these pictures and just lines or dots to do that. Also, an important reminder is that although in these Lewis dot symbols, we really only show the valence electrons in each of these atoms, there are other electrons, which are those core electrons, which are closer to the nucleus. But obviously, in terms of bonding, it is only the valence electrons which are important. It's only the valence electrons which are involved. And those are the only ones that we really do sort of show. All right. So another example would be water here. And if we look at water, just like our good friend fluorine here, we do see a couple things that are occurring. As we see on the bottom here, the fluorine does able to gain 8 electrons. And we see with our water that the hydrogen on the left, the hydrogen on the right, again, only should have 2 electrons, able to achieve that sort of helium configuration. And in this case, the oxygen, by sharing some electrons with the hydrogen on the left and some with the hydrogen on the right, able to achieve, again, that other magical number there, which is 8 electrons. Everybody there essentially achieves that noble gas configuration by sharing of electrons here. And that does lead us to those important rules that we sort of touched upon. But just to reiterate here, the Octet Rule is essentially means that everybody other than hydrogen, they essentially will continue to form bonds until everybody has 8 valence electrons around it. And again, the purpose of that is once they hit that 8 valence electrons, they have now achieved noble gas configuration and a very stable arrangement. The exception, and the one exception that we've been talking about here, again, is hydrogen should never, ever, ever, I'll say it even more, one more time, ever have more than 2 electrons. So if you find yourself drawing some hydrogens like this, double bonding some hydrogens, triple bonding some hydrogens. You know, just do yourself a favor, put a big X over it, because it is definitely wrong. Because hydrogen can only have 2 electrons. Hydrogen can only be on the outside, which means it should be on the exterior of bonding, and should really have only 1 line drawn to it, really no dots, unless you're not going to use the line and use the dots to represent the bond. But this is really the only way hydrogen should look when you're drawing Lewis structures. Again, very common. People like to throw dots all over hydrogen. Double bond, triple bond, hydrogen does not happen. Definitely going to be wrong. So keep that in mind. That's a very common mistake. Everybody thinks about, well, octet rule. But remember, when you look at the periodic table, hydrogen just needs to go 1 step forward to reach that noble gas configuration. Any questions on that there? No, helium will not have 8 electrons. It will not have, it doesn't have 8 valence electrons, if that's your question. Helium, which is basically number 2 on the periodic table, that 2, remember, is the atomic number, which means helium pretty much has 2 protons, which is basically 2 positive guys. So in a neutral helium, obviously, it can only have a maximum of 2 electrons to balance it out to 0. So just because helium has a grand total of 2 protons, that pretty much max out how many electrons that it could have. And that's why when we go past helium, sort of on the periodic table, the next kind of noble gases definitely has at least 8 electrons, which is neon is 10, and so forth. That's why really the octet rule sort of applies on the periodic table, you know, kind of after helium. And especially when we're talking about truly the octet rule really involves sort of covalent bonding. And that's because when we look at the periodic table, all of our nonmetals are over here, right? Kind of past, when we go past helium. And again, all those nonmetals basically just need to go forward to those noble gases underneath helium, which they all definitely do have at least 8 electrons. But helium itself maxes out pretty much at 2 because it only really has 2 protons. So at max, it can only have 2 electrons to balance out that charge. Other questions? Okay. So we sort of touched upon this, but just to reiterate, again, we could represent our bonding here in covalent bonding with those lines. And again, a single bond can be represented by 1 line, which represents the sharing of 2 electrons. Or you can represent it by 2 dots, obviously. A double bond, basically represented by 2 lines, are the sharing of 4 electrons. So in certain cases, for example, like CO2 down here, in order for everybody to achieve that octet rule, they need to actually make some double bonds on each side. So this oxygen is sharing these electrons here with the carbon. This oxygen on the right is also sharing. And what that allows is this oxygen to get to 8 electrons, this oxygen to get to 8 electrons. And by the carbon sharing with both oxygens, it's able for the carbon basically to get to 8 valence electrons. So sometimes, as we will see, and we'll talk about later on in this chapter as well, sometimes it is required that, you know, you need to double bond to get everybody to those sort of noble gas configuration and 8 valence electrons. Sometimes a single bond will do it, but sometimes you do definitely need more than that to sort of achieve that configuration. And sometimes you even need to make some triple bonds to sort of reach that. And again, a triple bond would represent by 3 lines that represents the sharing of 6 total electrons or 3 pairs of electrons. And that's what we see with nitrogen. In order for each of these nitrogens really to achieve noble gas configuration, they end up having to share 3 pairs of electrons for a grand total of 6. But each of the nitrogens, through that sharing of electrons represented by dots or obviously lines, are able to achieve that noble gas configuration. Again, on the bottom here, here's a triple bond between the carbons. which are necessary for it to achieve that noble gas configuration of 8 valence electrons, or octet rule. We also see our hydrogen, though, still only sharing 2 electrons, basically, again, allowing our hydrogen to achieve that helium configuration and be very, very stable. So sometimes it requires a single bond to do that. Sometimes it requires a double bond to do that. And sometimes it requires a triple bond to achieve that octet rule, that very stable configuration. We'll also talk about a little bit later on in this chapter as well, but sometimes people want to double bond and triple bond things like right out of the box when they're drawing covalent compounds and Lewis structures. And sometimes that's not really the best approach per se. You sometimes want to kind of follow certain rules or ways to draw these guys, which we'll talk about a little bit later on here. But keep that in mind. Again, sometimes people are a little heavy-handed on the double bonding and triple bonding of everything, kind of like right out of the box. Any questions on that so far? Okay. We are going to get into geometry and shapes and stuff like that. It's actually the next chapter is actually all that. So this chapter will pretty much be all about kind of bonding and drawing bonding. And then the next chapter, which is obviously related, we get into geometry, shapes, and polarity, and some other things as well. Other questions? Okay. So let's talk a little bit about, we're talking about this idea of sort of sharing of these electrons in covalent molecules. So what really is sort of the biggest maybe determination or determiner of, how these electrons are going to be shared? So sometimes these electrons, as I mentioned, are going to be shared pretty equally. And there's some times where these electrons will be shared unequally. And really that trend that we talked about a little bit earlier, which was electronegativity, is really kind of the main thing that we look at in terms of whether or not when we put 2 atoms together, would we expect those electrons to be shared equally? Would we expect them to be shared unequally? And we could also use electronegativity, although you don't really need to. You could use electronegativity to determine, will the electrons actually be shared at all, or will we get more of an ionic bond expected? So electronegativity is really important. And as we talked about before, the definition really of electronegativity is the ability of an atom to bring electrons towards itself. And if you remember, which is again the only thing really what I just wrote there and what I'm drawing right here that you need to know about electronegativity for the first exam is when we look at the periodic table, it increases as we go from left to right on the periodic table, with our good friend fluorine actually being the most electronegative element there is. And it does decrease as you go down. And if you remember that fits really nicely into those periodic trends we were talking about in terms of, as we go to the left and down on the periodic table, we have a lot of those trends where things really will want to give away their electrons. And that's where we find nonmetals, right? Left and down on the periodic table, as opposed to up and to the right on the periodic table. That's where we saw a lot of those trends where things really want to hang on to their electrons, bring electrons towards itself. And that makes sense because, again, that is essentially where we find our nonmetals up there on the periodic table. So we definitely can help, that's help, I guess. We definitely can use, I think is what I'm trying to spit out there. I think we could use electronegativity to help us make that distinction. I'm just going to go to sleep now. I'm going to stop talking. They'll make that distinction between how the electrons are going to be shared between those 2 atoms. And it also helps us determine, like I said, is it a covalent bond or is it an ionic bond? You really honestly don't necessarily need electronegativity to help you distinguish, is it going to be ionic or polar? It is almost a safe bet for our purposes here. If you're dealing with an ionic bond, you are probably dealing with a metal and non-metal like we talked about. So even though we kind of talk about using electronegativity a little bit in terms of helping us distinguish if it's an ionic bond, really just by knowing that you're dealing with a metal and a non-metal, that's pretty much enough to pretty much guarantee it's going to be an ionic bond. We're not going to have any type of sharing of electrons, but we will have that positive and negative attraction between them. But really where electronegativity really does help us out a lot is with our covalent bonds. And again, it's really because we're dealing with, as I mentioned before, two nonmetals. So it does help us decide, because these two nonmetals, they both really want to hang on to their electrons. It helps us decide whether or not we will have equal sharing of electrons, which is what is referred to as a nonpolar covalent bond, or if we have unequal sharing of electrons. So if we look at the couple of examples that we dealt with before, we had our hydrogen. And again, because they are both hydrogen atoms, we would expect, really, if we kind of badly draw here, and I'll say badly up front here, if kind of all this red smears the electrons, we would expect a fairly equal distribution of those electrons between those two elements. They're both the same element, which means if you think about it in a sort of a tug of war fashion, you have somebody on this side pulling, but you have somebody on the other side that's just as equal pulling on those electrons. And if you think about tug of war, it's like the little flag in between. If you're both pulling equally, like the flag's going to kind of stay right there in the middle, is not going to go anywhere. And that's sort of the idea here with our electrons. We got both of those hydrogens basically pulling on those electrons pretty equally to each other. Is not going to allow one to kind of overpull versus the other. And because of that, we would expect this equal sharing of electrons. And we would expect this to be a nonpolar covalent bond. Same thing would happen with our fluorines that we had earlier as well. Again, because both of these guys are fluorines, we would expect those electrons, again, sort of in the middle there, to basically be pulled to the right just as much as is being pulled to the left. And it would result in a perfect, if you will, equal sharing of those electrons between those two guys. So when we do have those equal sharing of electrons, that again is what is basically referred to as a nonpolar covalent bond. It is oftentimes just simplified as being called a nonpolar bond. Again, basically implying that it's a covalent bond, but some people will just straight out just call it a nonpolar bond versus a nonpolar covalent bond. They're both basically the same idea. But what happens though if we actually get a couple of guys that maybe are not the same elements, and maybe there's not the same sort of pull between them? So if we took like one element from each of those guys and we put hydrogen and fluorine together, what happens in that particular case? Well, when we put hydrogen there and our fluorine, now we definitely have two different elements there. And if you think about sort of their locations on the periodic table, fluorine is upper right, and as I mentioned before, it is the most electronegative element there is, which means when hydrogen and fluorine get together, fluorine's going to go, I kind of want to hang on to all those electrons. And you could have a little here, you could just kind of hang on just a little bit, but a lot of the electrons are going to go and basically hang over on the fluorine side. And in this case, what's going to result is, I don't want that, give me something right with there. There we go. It's going to result in unequal sharing of those electrons. And when we get unequal sharing of electrons, like we would here in this fluorine example, that is what is known as a polar covalent bond. are sometimes referred to as just a polar bond. So what is really happening though when we do that, or what is a sort of consequence of that unequal sharing? Well, if we look at our HF bond here, for example, if all of the electrons decided to kind of hang out on the side of the fluorine, that is going to create what is sometimes referred to as a partially negative charge being developed on the fluorine. That's a delta symbol, delta negative. That means a partially negative charge. And because all the electrons are kind of going away from the hydrogen towards the fluorine, the hydrogen is going to become more positive and build up a partially positive charge on the hydrogen side here. This could also be represented by what is sometimes referred to as a dipole arrow, where we draw the arrow pointing to the more negative side of the bond, and the one that kind of makes like a plus sign on the back end here to the more positive side of the bond. And these are two ways that we sometimes represent this sort of unequal sharing of electrons. This does not happen in our nonpolar bond. There is no separation of charge. You can almost think of these guys as being kind of neutral. There's no side that's more negative. There's no side that's more positive in a nonpolar bond because we have that kind of perfect equal sharing of electrons. It's only when we get this unequal sharing of electrons that we build up this kind of partially negative charge on one side, partially positive charge on the other. Any questions on that there? Now, a good question is, why is it partially positive and partially negative, these charges, and not like fully negative and fully positive? The answer is, in a covalent bond, there is still some aspects of sharing. So even though in this really bad case here, there's not a lot of sharing happening, there is still some aspect of sharing that's occurring, which means although the electrons are vacationing over here, they haven't decided to fully move there. And they are still hanging on by a little bit. So because there's still some aspect of sharing, that's why we refer to these charges as being partially negative and partially positive, because we have not had a full transfer of electrons, like, for example, we saw when we were talking about an ionic compound, like our lithium fluoride. When we talk about lithium fluoride, these are fully positive charge, fully negative charge, because there has been a full transfer of electrons from one to the next. Here we do not have a transfer of electron. They're still, hanging on a little bit, and there's still some aspect of sharing. Because it's unequal, we get those sort of partially charges that form on the side of the bond, but we don't get a full transfer of those electrons. Any questions on that? Okay. So this is sort of what I drew. I don't know, maybe I drew it better, but this again is that representation. If that pink is basically that cloud there, the greater the cloud there towards the fluorine side, going to make that more negatively charged, and the hydrogen more positively charged. Yeah, so for the most part, how can I answer that? Let me answer this sort of like this. Almost for the most part, when you're dealing with some different elements, and we're talking about here really non-metal and non-metal, this pretty much will occur. There's going to be probably some unequal sharing of electrons. There is actually some situations, and we're going to talk about it, I think maybe in a couple of slides down the road here, but there's actually a couple of situations, or a few situations, where it is potentially possible that you have two different elements that actually can share electrons equally. But probably most of the time, if you're dealing with two different nonmetals, I'll go 90% of the time. 90% of the time, it is probably almost safe to assume that they're probably not going to share the electrons equally. There will be some unequal sharing of electrons, but for sure there is actually situations, and we'll see them in just a second, where you actually can get two different nonmetals that, although they are different elements, they actually will end up sharing the electrons equally. And it's actually, as we will see in just a second, again, it is actually the electronegativity values that help us sort of decide that. Other questions on that there? So this is sort of the three different types of bonds, if you will. We have sort of on one end of the extreme, if you want to think about it, we have an ionic bond. And as I mentioned earlier, and which we talked about, it is definitely always between a metal and non-metal. It is always going to result in a transfer of electrons. And that's going to result in, as we talked about a number of times at this point, a cation that's positively charged, an anion that's negatively charged, and it's going to be that electrostatic attraction that's going to hold that together. That's just a fancy word for positive negative attraction. But again, the important thing, as we talked about, absolutely no sharing of electrons happening here. An example of that would be something like, say, sodium chloride. Sodium is a metal, chlorine is a non-metal. So when they come together, we would expect an ionic bond to form between those two. On sort of the other end of the extreme, we have a nonpolar covalent bond, or just a nonpolar bond, between two nonmetals. The important thing here is we're going to get equal sharing of those electrons. A couple of examples are like the ones we saw, H2, R, F2, of F2, R, F2. And sort of in the middle is like what we got drawn right here. We have our, I'll go right here, our polar covalent bond, or just polar bond. And this is also between two nonmetals. This also involves sharing of electrons, but it's unequal sharing of electrons. And obviously our HF there is an example of that. So on one end of the extreme over here, we have absolutely a transfer of electrons. On the other end of the extreme, we have nice perfect sharing of those electrons between the two. And in the middle, we have not perfect sharing of electrons, but not so unperfect sharing of electrons that they have been transferred. Sort of in the middle there, we got the unequal sharing of those electrons. Any questions on sort of the three different types of bonding that we're going to be talking about? Okay, so let's then talk about really, how can we determine, sort of where we're going to end up? Are we going to end up with an ionic bond? Are we going to end up with a polar bond? Are we going to end up with a non-polar bond? As I mentioned a couple of times, it is electronegativity that really is what helps us decide that. Electronegativity of an element is affected by a couple of those other periodic trends that we talked about. We talked about electron affinity. Remember, electron affinity is the energy change that occurs when an atom gains an electron. So up and to the right, that increases. Down and to the left, it decreases. Ionization energy is the energy required to remove an electron from an atom. Up and to the right, that increases. Down to the left, that decreases. And again, that's part of the two major trends as to why we see, metals losing electrons and nonmetals gaining electrons. So fluorine has a high electron affinity, high ionization energy. has a high electronegativity. I think I got an extra O in there. Sodium on the other side of the periodic table there, again, going to have a low electron affinity, a low ionization energy, and have a low electronegativity. So, how do we know? Well, a good guy by the name of Pauling actually came up with a method to use electronegativity values to help us decide, what type of bond would we expect to occur. He had developed this electronegativity values. He assigned elements values from 0 to 4, 4 being the most electronegative, 0 being not so much. And what we do is basically do delta En, which is sometimes referred to. That is the change in the electronegativity value. So we basically can calculate the change in the electronegativity values. And depending on the number that you get when you do that sort of change in electronegativity value as to what type of bond you would expect. So if we take a change in electronegativity value and you have it anywhere from 0 to 0.4, that is for the most part considered a nonpolar bond. Right? If you got above 0.4 to below 2, that is considered a polar bond. And typically speaking, if you are above 2 in the difference, that is usually an ionic bond. Again, you can really determine the ionic bond by what's there, but you could kind of use electronegativity values as well. Is it perfect? Well, not necessarily always perfect, but those are pretty much the cutoffs that we do here. If you have a difference in electronegativity value of 0, like on this guy, in addition to being a nonpolar bond, sometimes people will call that type of bond a pure covalent bond. And a pure covalent bond means basically I got like perfect sharing of those electrons happening here. So we could use these values, and it's as simple as basically subtracting the two numbers. Make sure you get a positive number, but subtract the two numbers, and you can kind of determine that. So here's a table, and you have a similar table, I think, in your book, of some electronegativity values on the periodic table. We see the general trend that we talked about. As you go up and to the right, we see higher electronegativity, left and down, lower electronegativity. We see upper right corner is fluorine, which is number 4, or a value of 4. It's the most electronegative. You may be asking, what about our good friends, the noble gases, which are to the right? So if you remember, noble gases are chemically inert, which means they really don't react with things. They don't react with things because they are pretty happy the way they are. And as we just saw a little bit earlier, the goal of all this bonding is for everybody to become just like the noble gases, which means, they're trying to get to the noble gas configuration. Noble gas is really not interested in doing any type of reactions and stuff like that. So we typically don't have electronegativity values for noble gases. They're kind of thought of as 0, again, because they're really sort of perfect the way they are in that sense. So let's take a look at how we could kind of use this. And why don't we look at the 3 sort of examples that we saw just a second ago when we talked about the different types of bonding. So we had our sodium chloride, right? We had our HF, and we'll do F2, why not? So if we were going to use these electronegativity values here to help us determine what type of bond we would expect, again, a reminder that the sort of cutoffs and stuff that we're looking for, the change in electronegativity value of 0 to 0.4 nonpolar, basically 0.4 above to below 2 is going to be polar, And again, typically above 2, not perfect in all cases, is going to be ionic. So if we go look at sodium, its electronegativity value is 0.9. If we look at chlorine, its value there is 3. So if I calculate the change in electronegativity, basically I take 3 minus 0.9. That gives me a value of 2.1. 2.1 is definitely above 2, and we would know that this is an ionic bond like we did predict it would be. Any questions on that one there? If we go to our other extreme there, that is fluorine, which has an electronegativity value from the table of 4. This fluorine also would have an electronegativity value of 4, which means if we do our change in electronegativity, that is 4 minus 4, which is 0. That is definitely right there. It's really a pure covalent bond, but that is going to be a nonpolar bond because of that difference in electronegativity here. And if we look at HF, H is 2.1, F is 4. So again, if we do our change in electronegativity, that is 4 minus 2.1. That's a lot of math. I'm going to go with 1.9 and hope for the best there. 1.9 puts us right here, almost at the edge, but still below 2. And it is a polar bond. We could also see that there is not very much equal sharing happening here. But again, there is still that little hanging on of some type of sharing that is occurring. So when we're trying to determine, what type of bond are we dealing with, electronegativity values are important to help us do that. If you don't have the values given to you, a lot of times you can use the general trends on the periodic table to help you decide, and you'll usually be pretty right. But we definitely can use these values to help us determine, what type of bond we are dealing with. Any questions on those guys there? Okay. So why don't you try a few here? Why don't we decide, is it polar, nonpolar, or ionic? If we have a bond between, let's say, carbon and oxygen. Let's go with carbon and sulfur. Let's do let's do cesium and oxygen. Let us do phosphorus and nitrogen. And let us do carbon and hydrogen. For each of those, using the electronegativity values, take a minute here or so and figure out what type of bond would we expect based on electronegativity. Therefore, electronegativity is 2.5. Oxygen is 3.5. So again, if we take the difference in electronegativity, that's going to be 3.5 minus 2.5. That will give us a difference of 1. 1 would put us in this range between like 0.5 and 2, and we would expect this to be a polar bond between those two. Any questions on that particular one? Let us then look at P and N. So P and N, P is phosphorus, which is 2.1. N is nitrogen, which is 3. So we would take the change in electronegativity. That's going to give us 3 minus 2.1. That's going to give us a 0.9 difference. That 0.9 difference also going to put us between basically 0.5 and 2, which means we would expect this guy also to be a polar bond. Any questions on that one there? All right. Then let's take a look at carbon and sulfur. So if we take a look at carbon and sulfur, carbon again being a value of 2.5 for electronegativity, sulfur being a value of 2.5 for electronegativity. Change in electronegativity is going to be 2.5 minus 2.5. That is going to be 0, which puts us right there. This is a nonpolar bond. So this answers, I think, somebody's question a little bit earlier. This is a case where you can have two different elements that actually will share the electrons equally because of its electronegativity value. Why does that happen? If so, let's just take a moment here to talk about really why that sort of happens. It is what is sometimes referred to as the diagonal rule, like on the periodic table. And what that means is if we look at the location of each of those guys, so we look at carbon's location and we look at sulfur's location, they are essentially diagonal of each other on the periodic table. And what that means is, although carbon is further up on the periodic table, sulfur is further to the right on the periodic table. They essentially cancel each other out in terms of their electronegativity effect, if you will. So although they are different elements, just because of their sort of location there on the periodic table, one is further up, but yet one is further to the right. And again, that basically cancels the difference between them. We see that in several sort of locations. For example, if you look at boron and you look at AS, again, diagonal of each other, we see that. We also see it with nitrogen and chlorine. We see that diagonal sort of relationship that occurs. So again, we do see a number of those sort of diagonal relationships that occur. And sometimes you can, as this example pretty nicely demonstrates, you can have two elements that are different, but still able to share the electrons equally. You could also have two elements that are different and will not share the electrons equally. But the one thing for sure you would know is if you have two of the same elements like F2 or H2 or N2, those are always going to share the electrons equally because they basically have the same electronegativity values. So, you know, it's not an automatic, as I think the earlier question was asking, will we always get sort of that unequal sharing of electrons between two different elements? I won't say it's 100% because obviously it's not. But, you know, high 90s probably, it's a good chance you're probably going to get some unequal sharing of electrons. But there's definitely positions where you could get two elements that have the same electronegativity values and will share those electrons equally. Any questions on that there? Okay, so we did that. Let's talk about carbon and hydrogen then next and see what's happening there. So carbon is again 2.5, hydrogen is 2.1, which means the change in electronegativity going to be 2.5 minus 2.1, and that's going to give us a 0.4. That is actually right there at the cutoff of nonpolar. If I can get this thing out of my way, excuse me, come here, there you go, come on. So right here, I'm trying to get over there, at the cutoff of nonpolar, and it's actually why the cutoff is 0.4. This is going to be nonpolar because the carbon-hydrogen bond is considered a nonpolar bond. It's really the basis of all organic chemistry, and we wouldn't have organic chemistry if that wasn't sort of the cutoff. So kind of the 0.4 is because of the carbon-hydrogen bond is the cutoff for nonpolar. So it is still considered a nonpolar bond in this case. Looking at our last one, which is cesium here and oxygen, that is 0.7. Oxygen is 3.5. It's late. I'm going to grab my calculator and go with it. That is like a 2.8. Good thing I grabbed the calculator there when we do that difference. So that is definitely above 2, and that would definitely mean that it's ionic. And to be truthfully honest with you, as soon as you see that's a metal and that's a non-metal, you don't even need really the electronegativity values. Any questions on any of those examples or how to use these actual values? They would obviously be given to you on an exam or quiz if you needed them. But you do need to obviously know how to use them, I suppose. Any questions on how to figure those things out? Okay. So earlier, just to wrap it up on sort of this conversation here, earlier I was talking about the idea that, if you're not given the sort of electronegativity values here, and you have a question of, is this going to be a polar bond, a non-polar bond? There are some situations where you really do not need the table to figure that out. So let's take a look at a couple that we did, the carbon-oxygen bond. This is carbon here. This is oxygen here. They're actually in the same period on the periodic table, which means as we go this way, it increases in electronegativity. So just by knowing they're in the same period, oxygen is further to the right than carbon, we will know that they are probably not going to share the electrons equally. There's no diagonal relationship happening here because they're in the same period. And we could just very safely assume that this would be a polar bond because of that. We could also very safely assume that this guy would be more negative and this guy would be more positive, again, because of his position in the same period, with oxygen being further to the right. Any questions on that there? If we look at our phosphorus and nitrogen, phosphorus is here, nitrogen is here. These guys are also in the same group. And what we see is going up, right, is more electronegative. So we would expect that the nitrogen being more electronegative than the phosphorus. And we could also, just by looking at its location on the periodic table, make a pretty safe bet that that's going to be polar. And again, nitrogen being further up would be more negative and more positive for our phosphorus. So sometimes, especially when you're dealing with elements that are in the same period or elements that are in the same group on the periodic table, you pretty much don't need the actual numbers. You can safely assume, based on the periodic trends of electronegativity, this guy will be more electronegative or this guy will be less electronegative. And again, you could very safely assume it's going to be a polar bond versus a non-polar bond. Question on that sort of use of the periodic table and figuring things out. The one last thing I will say here before we wrap it up here for lecture is what we are looking at right now when we look at electronegativity values, for the most part, is usually what is referred to as bond polarity. And bond polarity, when we use the electronegativity values, really for the most part, if it is something that is not a diatomic molecule, if it's a diatomic molecule and there's only one bond, it actually tells us some other things. But if it's more than basically one bond in the molecule, we use electronegativity to tell us the bond polarity. And it basically tells us, specifically speaking, between this element and this element, those electrons that are being shared, are they going to be shared equally, unequally, or will we have a transfer of electrons? And that's really what we use these electronegativity values for, to tell us specifically between those two elements how those electrons are going to be shared. There's something known as molecular polarity, which we'll talk about later on in the next chapter, that talks about the entire molecule as a whole. But usually when you're using electronegativity values, they're typically for just between two elements and a single bond. Also can be used for diatomic molecules, as we'll talk about later, but that's usually what we're talking about here. Any questions on that? All right, we use good place. We will stop here for today. We have lab at 7:10ish there, and we're doing study assignment A, which is the one we kind of pushed it back as well. So that is significant figures, conversions, and stuff like that. So we'll talk a little bit about that stuff just to make sure everybody's sort of on the same page. And then that's pretty much what we got on tap for today. A reminder again that our exam is 1 week from today on chapter 1, 2, and again from 3. Not this electronegativity, but as we talked about it in chapter 2-ish, if you will, the general trend in electronegativity in terms of increasing up and to the right, decreasing down to the left, and what electronegativity is all you need to worry about in terms of electronegativity for exam 1. This stuff that we just did today in terms of electronegativity, that will be on exam 2. So that's where you have to worry about that stuff. Any questions on that? All right, I'll see everybody in about 15 minutes or so in lab. Make sure you put here if you haven't